Today, I'll be talking about the abelian group. First of all, let's talk about what a group is. But before that, let's talk about the legacy of the great mathematician Abel, for which this is named. So he was a Norwegian mathematician, after which the Abel Prize is named, and he was the first one to discover that a quintic polynomial is generally unsolvable, but more so, he also discovered abelian groups, or rather defined abelian groups. And they turn out to be really useful in several applications across math and science, including topology. So first of all, let's talk about what a set is, because that's the most fundamental thing we need. So what is a set? Set. Great. So a set is a collection of multiple elements. And these elements could be anything. They could be scalars. They could be vectors. They could even be other sets, even though that last one is very rarely used. So a set is a very unique thing, and it's basically the mathematical term for a collection of things. So for example, the set of whole numbers would be 0, 1, 2, 3, etc. Set of whole numbers, by the way. I don't feel like writing the negative numbers today. This is also known as... might as well put the blackboard bold. So, a countable set is what we call a set where we know what the next element is. So, for example, if we're talking about the multiples of 17, and I say 17, 34, 51, you can tell me what the next element is, right? It's obviously 68. You just have to add 17 to this one, or maybe you've memorized it by heart like me. So, this is a countable set. But what about an uncountable set? An uncountable set is something like the rational numbers, where you do not know what the next element is. So 0 is a rational number, but what comes next? Is it 1 over 100? No, there's something smaller than that. 1,000? No, there's obviously something smaller than that. 10,000? And this keeps going and going. You don't quite know what the next element is, given one element. You just know what is in the set and what is not in the set. So this constitutes most sets. So today we'll be talking about groups. Now, groups are not quite sets. Rather, they're a special kind of set paired with an operation. Now, when you hear operation, you might think about the 4, or maybe even, if you really want to be like that, 5 operations that you learned in middle school and high school. If you don't know, this is the exponentiation one. Could I count log as one? No, I wouldn't count log as an operation. But whatever, it doesn't quite matter. So, these are binary operations, and they're what we'll mostly be using. Binary means that we put one number in, then the operation, and then the other number. So, for example, A times B, A plus B. Sometimes we may stylize it because writing this out doesn't look so good, so we might write this instead. But the meaning stays inherently the same. So we can define any sort of, any operation. For example, consider an operation represented by this symbol, such that something like this happens. And we don't even have to make it so that they are binary. We can have these operations happen to just one element of the set. Talk about what an abelian group is now. Now, a group is special in itself. A group is very special. So a group is a set paired with its own operation. Now, for the non-abelian group that we're going to explore, this operation is adding, as in adding rotation. So, now the criterion for a set plus its operation being a group is, first of all, this has to be associative. I.e., that means that if we have A operation B parentheses operation C, this should be equal to A operation parentheses B operation C. If you write the cross product like this, I'm so sorry for your family's loss. So, this is what associativity means. Now, what about the conditions for the set? Well, for the set, it must contain the identity, and an identity must exist in the first place, of this operation. So, for example, an additive identity is 0, because any number plus 0 is itself. And a multiplicative identity is 1, because k, any number times 1 is itself. Now, it must also contain an inverse for the operation. So, for example, the additive inverse of k was negative k, because when you add them together, you get the additive identity. And the multiplicative inverse is 1 divided by k, because when you multiply them together, you get the multiplicative identity, 1. So, it must contain the identity of and the inverse operation. So, the inverse of every element existing in the set. So, let me give you an example of a group. So, an example of a group could be 0, -1, 1, 3.5, minus 3.5 under addition. Now, why might this be a group? Well, first of all, addition is associative, as I'm sure you all know, but also the identity is here, the additive identity being 0, and every element in the set has its additive inverse involved as well. So, that makes this a group. Now, is it an abelian group? An abelian group is when the operation is commutative. It's okay. There are more black holes. So, now, let me give you an example of, I already just gave you an example of an abelian. Addition right here, as you should all know, is commutative. So this right here is an abelian group. But most operations that are associative, at least the ones that I could think of with my tiny little brain, are also commutative. So, because the only things we usually think of when we hear that kind of stuff are compositions of addition and multiplication, which all end up being commutative or commutative and associative on their own. So they always form abelian groups. So what's the exception here? As I said, rotation. Welcome to SO3, one of the most famous non-abelian groups that's widely used in physics. So this is simply the set of rotations, every single rotation that you could perform around the origin in three-dimensional space. Now, first of all, this is obviously associative. So let's say we had a 30-degree rotation around theta, and for reference, I'm pretty sure theta is in this direction, and is it? No, I'm pretty sure theta is in this direction, and phi is in this direction. So, 30 degrees theta plus 60 degrees phi plus 60 degrees theta. Let's imagine how that would look like. So now, let's draw this straight vector and then rotate it by 30 degrees theta. That would look sort of like this, 30 degrees. Then 60 degrees phi, which would look like this, 60 degrees. And then we want to rotate it 60 degrees theta again, which would make it look like this. So this is the final landing point. Alright, let's keep note of that. Now, let's try doing it as 30 degrees theta plus 60 degrees phi plus 60 degrees theta. Oh, and note that the set that forms this group is also uncountable, because you don't know what's the next rotation. It's essentially analogous to the real numbers, but multiplied by 2 because of phi. So, what's this? Well, let's try adding those rotations together as well. So, our starting vector is right here. Then 30 degrees theta is going to land them in this direction. And I think you can see the point. We're just doing the same exact sequence of rotations to get the same exact results. No? So, that means that this is fully associative. But is it commutative? Well, I'll show you. You don't have to go outside the room. Alright, so that looks nasty. Alright, so first of all, let's set rotation A. So let's set rotation A to be, say, in this direction, so 90 degrees theta, and rotation B to be minus 90 degrees phi. So, now, let's draw this vector right here. This is going to be 0, 2, 1. For reference, this is y, this is the x, and that's the z. 0, 2, 1, right? So now, let's see if RA of RB of y, or of v, is equal to RB of RA of V. So RA is 90 degrees theta. So that's going to be in this direction, to rotate it over here, which means we have this vector now. This vector, if you look at it carefully, is 2, 0, 1. Now, minus 90 degrees phi is going to land it right over here. So that's going to be, let me look at this again. Okay. So let's see. What have I done here? Alright, so that seems good to me. So we have that, and then we use RB to lower it down over here to get this. It's not the most accurate drawing in the world, I know. But it should be approximately 210 or 120. I can't quite tell from this drawing. Let me actually see. Yeah, it's 120, sorry. And alright, so we are not done yet. Okay? Now let's grab the other colored chalk to see what happens if we reverse that direction. Whose freaking coffee mug is this? Okay, so here's the other chalk, also pretty small, but it's a different color, so there's that. So now we also have 0, 2, 1. Now we rotate that minus 90 degrees phi, so that's going to be right over here. That's now going to be 0, minus 1, 2. And now we have to rotate this 90 degrees over theta. This is going to be a little tricky to do, but let's draw this in a more accurate fashion. So that's how it looks like, and then we have to actually somehow rotate this 90 degrees around theta. So that's going to end up right over here, I see. So, yep, in this direction. So this is going to be in the negative x direction, actually. This is going to be minus 1, 0, 2. And as you can see, the results we get are completely different from each other. Minus 1, 0, 2, 1, 2, 0. So in terms of adding rotations, there is no sense of commutativity. Okay, just making sure I have the right amount of t's. So yeah, that's abelian groups, non-abelian groups, sets, and groups in general. That was a pretty good lecture. Thank you. Here is our abelian group, and here is our non-abelian group. That's it.